This is a second video clip on the lecture of regression. So here we start with an example of regression, of linear regression, a house price versus size of house. So usually we consider house price as a dependent variable and size of house as an independent variable. Obviously, the larger the house, the higher the price. That's the usual case, right? So let's see if we can quantify this relationship between size of house and the house price. So here we have our sample data set. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 observations, so 10 houses. And Y is per thousand dollar, okay? That's the price, $45,000. That's for house one. And the size of the first house is 1.0 multiply 1,000 square feet, which is 1,000 square feet, right? So obviously, we surveyed 10 houses. We have their prices and also we have their sizes. Okay, so size is X, price is Y. We want to find out a specific function. Y is equal to A plus BX to quantify this relationship. Okay, so we need to find out A intercept and B slope. So here we go. So we list everything we need here, use several columns. So the first column, column 1 is for Y. Column 2 is for X. So observations there here. Column 3 is the difference between each observation of Y and the mean value of Y. Similarly, column 4 is for the difference between each observation of X, which is size, and the mean value of X. And column 5 is the product of column 3 and column 4, right? Column 6 is the squared column 3. Column 7 is the squared column 4. Okay, according to these values, we can find out the mean value for Y, which is the mean value for price, and the mean value for house size or X bar, right? And this is also what we want is a product between the difference between Xi and the X bar, and also the difference between Yi and Y bar. We calculate the sum. Basically, it's the sum of this specific column, column 5, right? Sum of it. And we also need to find out the squared sum of the difference between xi and x bar. Okay, once we have them, we can use these two formulas I introduced in the last part of the first video to find out B and A. Okay, so eventually I will just I'll just jump to the conclusion. Okay, so here we have B, which is slope 36.6, and A as the intercept, which is 6.8. So eventually, the formula or the function we have here is y equals 6.8 plus 36.6 multiply x. So that's a quantified relationship between house size x and house price y. Okay, so again, it's not a very complex process of calculation, but you need to be careful with wisdom. You need to be patient. And let's just use another view to address regression. Okay, we can use a view of partition to do that. So partition the variability in y into two parts. The first part is the variability that can be explained by the regression line or by the regression function. And there is a second part, that's a variability that cannot be explained or unexplained by the regression line. Obviously, the first part is the part we want, because we want to use that linear function to explain the variation of y using x, right? And the second part is something we do not want. it can be addressed by residual. It's a variability that cannot be addressed by your regression function, linear function, right? So we use different say indicators to address them. So we use SSR, regression sum of squares, to address the variability explained by the regression line. Okay, it's about the difference between the predicted value and the mean value. So SSE, on the other hand, residual sum of squares, it is used to quantify the variability unexplained by the regression line. And this is related to the difference between the actual value or observed value and your predicted value. This difference is actually residual, right? We define it. This is residual. Obviously, if you add them up, you have SST, total sum of squares, right? If you add SSR and SSE up, you have SST. And SST can be calculated as the sum of these two indicators, SSR and SSE. Or you can simply use the difference between observation and mean value to calculate SST. Obviously, SSR is something we want, so the larger the better. SSE is about residual, so the smaller the better. Okay, so we can define another indicator to quantify the performance of our regression model or regression function, that linear function y is equal to a plus bx. We want to evaluate its performance using something called coefficient of determination. And we use R squared to address that. So coefficient of determination, R squared, it's the ratio between SSR and SST. So SSR is something we want, the variability of y that can be explained by your regression model. SST is the total, right? So the larger the better, okay? The larger this ratio, the larger this proportion, the better the performance of your regression model. So R squared, obviously, it's equal to or larger than 0. So it varies from 0 to 1. And the larger the better. If your R squared value is equal to 1, then X and Y, they are perfectly explained. The relationship between X and Y is perfectly explained by your model, which is not likely to happen in real data sets, okay? But from 0 to 1, for R squared, the larger the better, okay? If you have an R squared value of 0.8, it means that 80% of the variability of your dependent variable can be explained by this model, which is pretty good, right? 80%. And as Euro, we can still do significance tests for R squared. So hypothesis is that, a null hypothesis is that rho squared, okay, the population version of R squared is equal to 0. And alternative test is that rho squared is larger than 0. Okay, so this is a one-sided test, right? Because the alternative hypothesis is something larger to 0 instead of not equal to 0, right? So here we have a new statistic. It's still F, but with another, with another way to calculate it. It's about R squared and N. N is the number of observations. R squared is the coefficient of determination. Okay, and the critical value is F alpha. Be careful, this is not half alpha because we're doing a one-sided test, right? Alpha and 1 and N minus 2. Okay, how to do this? How to do this test? You can still use a table, for example, a table to help you, just like what you did for ANOVA, right? So you need to calculate SSR, SSE, and SST, right? So the degree of freedom for SSR is always 1. That's the reason why here it's alpha 1 and minus 2. So 1 is the degree of freedom for SSR, and n-2 is the degree of freedom for SSE. Okay, so mean square SSR, because it's the ratio between SSR and 1. So basically, it's still SSR. So mean square for SSE is the ratio between SSE and its degree of freedom, right? And eventually, F-test is the ratio between mean square of SSR and mean square of SSE. So you have this formula eventually, okay? And so you have two ways to do the significance test for R square. One is using this table, which is pretty straightforward, right? You just need to calculate SSR, SSE, and SST first, and then just fill out the table. And another way is using R squared to do that. Obviously, you need to calculate R squared here, okay? So let's just use another example to address that, okay? Let's just assume we have A intercept as 17.8, slope B 1.171. So your prediction model or your linear function is like this. Yi hat is equal to the intercept plus slope multiply xi, right? So this is a formula you have, right? So we have yi, xi, a predicted y, and the different squares here listed in this table with 5 columns, right? So in order to do the test, we need to calculate y bar, x bar, and these two sums. Okay, these two sums. And we first calculate R squared, right? So R squared is the ratio between SSR and SST, and this is the formula I showed you before, right? So we're going to use these two sums we just calculated to calculate R squared. So eventually 0.6966, that's the result. So it means that 69.66% of the variability of y can be explained by this model. I would say it's good. It's not very high. It's not 0.8 or even 0.9, but it's very close to 0.7, which usually is a pretty good performance for linear regression. Okay, so after R squared, we want to do the significance test, right? So SSR, SSE, SST, right? Degree of freedom, always 1. Degree of freedom, n is equal to 10. So 10 minus 2, 8. You just follow the procedure and you get an F-test value, which is pretty big, right? And you go, and then you need to find the critical value for F, right? You go back to the F table using alpha, let's just say 0.05. Of course, you can change it in your specific research or application, right? 0.05, 1, and 8. That's 2 degrees of freedoms, right? And the critical value is only 5.32. So your test value is larger than your critical value, which means you need to reject the null hypothesis, right? Okay, I will just stop here, and there will be the third video clip for this lecture, and I will see you later. Thank you.